is something like this. Okay, we have the square root of 75 over 12. So remember, the word rational is referred to because we're talking about a fraction, ratio. And when we're taking the square root of a fraction, we can actually think of taking the square root of the numerator and the square root of the denominator. So we can think of the square root of 75 and the square root of 12. Now we want to be able to simplify those square roots. So I'm going to focus on each of those separately. Notice that 75 and 12, neither of these is actually a perfect square. But you might notice that 75 is divisible by the perfect square 25, and that's going to help us to simplify. The technique that I'm going to use translates nicely when we actually work with variables. Before we go on and look at that, I want to just make sure that you guys can hear me. So I'm going to type in the box, can you hear me? And if anybody could answer, that would be great. So we're going to use the same prime factorization idea that we used when we were looking at greatest common factor. 75 is 3 times 25. Oh, thank you, Danielle. I appreciate it. I'm glad you can hear it. All right, and then 3 is prime, so that branch of the prime factorization will stop. Oh, it looks like my stream health is getting bad here. Hold on a sec. Okay, I hope you can see the video because it's telling me that we're having trouble with our streaming. But anyway, we want to continue until we get to prime factors. 25 is not prime, but it can be written as 5 times 5, and both of these are prime. And so we see that 75 can be written as 5 squared times 3. 3 times 5 times 5, or 5 squared times 3. So what I'm going to do is I'm going to think about simplifying the square root of 5 squared times 3. And then for 12, 12 can be thought of as 3 times 4, and of course 3 is prime, but 4 is not. But 4 is 2 times 2, which 2 is prime as well. Remember, prime just means divisible by itself in 1. 2 is actually the only even number that's prime. All the other even numbers are divisible by 2, so they're not prime. In any case, we're going to have 2 squared times 3. So we have the square root of, instead of 12, we're going to think of it as 2 squared times 3. Okay, and then when we take the square root of a product, we're actually allowed to split it up into the different factors. So we can take the square root of each part of the product. So square root of 5 squared times square root of 3 over square root of 2 squared times square root of 3. Now what happens when you take the square root of a perfect square? What's the square root of 5 squared? In general, if you take the square root of any number squared, let's call the number a, and I'm going to assume a is a positive number, by the way, you're going to just get a back. It's kind of like the square root with the index of 2 cancels with the power of 2. So what we're going to get is just, instead of square root of 5 squared, we're going to get 5 square roots of 3 over 2 square roots of 3. Now notice square root of 3 divided by itself is just 1. So we just get 5/2. And I think I need to fix my PowerPoint. It's just too small, so I'm going to do this. Okay, so if you have any questions, again, you can type them into the chat. Now, I'm going to work the same problem a different way on the next slide. I wanted to show you that you can use the prime factorization method, but in this case, you could actually simplify the problem quite a bit if you notice something right at the beginning. So let's try this one more time. So again, we're looking at the square root of 75 over 12. So if you notice right at the beginning that you can reduce this fraction, you're going to save yourself quite a bit of work. So what I mean by that is 75 is 25 times 3, or 5 squared times 3 as we wrote a minute ago. And 12 is 4 times 3. So they have a factor of 3 in common. So those 3's divide out to leave just a factor of 1. So now we're taking just the square root of 25/4. So that's the square root of 25 over the square root of 4, which is 5/2. So either way, we get the same answer, but notice it was a lot simpler. In some problems where you can reduce like that, you can do something like this. In other problems, you're going to have to go the longer route. Okay, now I'm going to pull up another problem for us to look at related to radicals. Okay, so this one is going to have variables in it. So you're going to see something that says simplify, and it'll say something like the square root of 36y to the 14th power. Okay, 36y to the 14th power. It also says assume that the variable y represents a positive real number. So y is a positive real number. I'll explain why it says that in a minute. Okay, but for right now, let's just focus on the mechanics of simplifying this expression. So if you know right away that 36 is a perfect square, that's great. If you didn't, you could use the prime factorization method. So I'm going to pretend for a moment, just for the sake of argument, that we didn't know that 36 is 6 squared, okay? So let's say somebody came in and said, okay, well, 36 is 4 times 9. Neither of those is prime. But 4 is 2 times 2. Those are primes. And 9 is 3 times 3. And those are primes. And we could say 36 equals 2 squared times 3 squared. Remember, the square root of a perfect square cancels out the power. So knowing that this has factors that are perfect squares is really nice. So what we're going to do is we're going to have, instead of 36, we're going to have 2 squared times 3 squared. All right, and we'll deal with those in a minute, but I also want to point out that y to the 14th power is also a perfect square. Do you remember that when we raise a power to a power, we multiply the exponents? For example, if we had y cubed and we squared it, we would get y to the 6th. Or if we had y to the 4th and we squared it, we'd get y to the 8th. That's supposed to be a 4. So what do you think you could square in order to get y to the 14th power? Well, remember, whatever that number is, when you square it, you have to multiply the exponents together to get y to the 14th. So what do you multiply times 2 to get 14? That would be 7. So you can think of y to the 14th as y to the 7 squared. So when why is that good? Because remember, when you take a square root, the index is 2. We're asking what squared gives you that number. So breaking this apart, we have what squared gives us 2 squared. Well, that's just going to be 2. What squared gives us 3 squared? Well, that would be 3. And what squared gives us y to the 7th quantity squared? Well, that's going to be y to the 7th. So we have 2 times 3 times y to the 7th, or 6y to the 7th. Now, if when you looked at the square root of 36, you knew, okay, that's 6 squared, you could immediately jump to the 6 here. And a way to get directly from the square root of 36y to the 14th to 6y to the 7th, the square root of y to the 14th, you can just divide the index by 2, because that's really what you did when we tried to figure out what squared gives you y to the 14th. I had to say, well, what would you multiply by 2 to get 14? That's the same as saying what's 14 divided by 2. So you can get So let's work a similar example, and instead of going through all of these steps, let's see if we can kind of skip to the end. So for example, if I said the square root of 100 z to the 18th, well, if you happen to recognize that 100 is a perfect square, you don't have to go through the prime factorization. You can just think, okay, what's the square root of 100? What's the square root of z to the 18th? Square root of 100 is 10, and square root of z to the 18th, you divide by the index 2. It's not written, but it's 2 there. So 18 divided by 2 would be z to the 9th, 10z to the 9th. So that's how you work on the problems where you're taking square roots of perfect squares. Now I said I would explain why we assume that the variables in these expressions are positive real numbers. So let's look at that real quick. Hi Shamar, thank you for logging in. So one thing you have to be careful about, it's a very tiny detail, but every once in a while it sneaks up and bites you, and that is that when you take the square root of a perfect square, you don't always get the original number back. And here's what I mean. The square root of 5 squared, in other words, the square root of 25, is just 5. But let's look at the square root of negative 5 squared. So the square root of negative 5 squared is actually also the square root of 25, which is 5, not the negative 5 that we started with. So it would be incorrect to assume that if I took the square root of an unknown number squared, that I would get that number back. Not necessarily, because if that number was positive, yes, I'd get the number back, but if it were negative, I would get a positive version back. So it's more appropriate to say that the square root of x squared is the absolute value of x. Remember, absolute value just means distance from 0, and it has the effect of changing everything to a positive. So this goes, by the way, not just for square roots, but when we start in a few minutes looking at, say, the 4th root of x to the 4th, or any even root, unless someone has assured you that that variable is positive, you can't assume it is. So in both cases, you'd have to write absolute value to make sure that you're being accurate. Okay, and so we'll see a few of these pop up where that matters, but for the most part, we're going to tell you that the variables are positive so that you don't have to worry about the square root. Okay, hold on just a minute, please, guys. I have a little interruption. Sorry guys, the volume was off. Sorry about that. So what I was trying to explain is that if you take the square root of a negative number, it doesn't work in the real number system. There's no real solution. And the reason is because when you take a square root of -9, you're looking for a number that multiplies times itself to give you -9. But if you multiply -3 times -3, you're going to get a positive. And if you multiply +3 times +3, you're going to get a positive. Anytime you multiply a number by itself, you get a positive. So when you do your ALEX work, you'll see that you have the option of saying no real solution for a number like that. But that happens because we have an even number of negatives being multiplied together, resulting in a positive. And this was an even index. So this happens when you have an even index and a negative under the radical, a negative radicand. But when it's odd, like cubed root, we don't have that problem, because if you multiply 3 negatives together, you can in fact get a negative. So what number can you multiply times itself 3 times to give you -64? That would be -4 times -4 times -4. Okay, now if you were using the prime factor method because you didn't realize that -64 is -4 cubed, you could work it as follows. You would take 64 and you would factor it into 8 times 8, and then 2 times 4 and 2 times 4. And this is supposed to be a 4 here. And we have the 2's are prime, but the 4's are not, so we'd have to keep going. So we'd have 2's and 2's, 2's, 2's. Okay, so we have all together 1, 2, 3, 4, 5, 6 factors of 2. So you could think of this as the cubed root of -2 to the 6th power. And remember how we just said that you can actually divide the power by the index if it goes in evenly. So you would say, okay, that's -2 to the 6 divided by 3 power, which is -2 to the 2nd power, or -4. And you would get the same answer that way. Okay? So it's kind of like you're going to resort to this longer method when you have, if you don't immediately see the root yourself. If you can't think of a number cubed that gives you -64. All right, let's look at one more. What if I asked you for the 4th root of -16? Okay, so for that one, you would immediately say, well, I have an even root. That would mean it's asking me for some negative number multiplied times itself 4 times to give me a negative, and that can't happen. So you would say that's not real. On the other hand, if you had -4th root of 16, this is a different story altogether. The -4th root of 16, well, what can you multiply times itself 4 times to give you 16? Hopefully you said 2, but let's say that you were not sure. So you could just factor it out. 2 times 8 is 16. 2 times 4 is 8. 2 times 2 is 4. So we have how many factors here of 2? We have 16 equals 2 to the 4th power. That's convenient. So this negative is just going to tag along, and we have the 4th root of 2 to the 4th power. Remember, divide the exponents. So that's going to be -2 to the 1st power, or -2. Okay, so 2 different scenarios. If the negative is inside the radical and you have an even index, it's not a real number. But if it's outside the radical, you can just have that negative tag along. Remember, you can tell me if I'm going too fast, and you can ask questions through the live chat box. Okay, let's look at another question with roots. So what if I asked you to simplify and I gave you the cubed root of 8 over 125? Okay, well, first of all, whenever you have a square root, cube root, any kind of root of a fraction, if you want to, you can separate it into the cubed root of the numerator over the root of the denominator. So you can think of it, you can kind of focus yourself on one task at a time. Makes it a little less complicated. By the way, I should have said this out loud, but mentally I kind of looked at that and said, there's no factors in common, so I can't reduce that fraction first. Okay, then what would I do next? Well, if I recognize that I have a perfect cube, 8 is a perfect cube, the cube root is 2, I can just write that down and we're good to go. I also recognize that 125 is a perfect cube. You can write out your perfect cubes, by the way, along the side of your paper, so you can recognize them when they pop up. But let's say that you didn't. You could do the factorization. So trying to find the cube root of 8, you would say, well, 8 factors into 2 times 4, and that's 2 times 2, so we have 3 factors of 2, so 8 is really 2 cubed. And then for 125, whenever something ends in 5, it's divisible by 5, so you could start by saying, okay, 5 goes into that how many times? And you would get 25. And then how does 25 factor? 5 and 5. So 125 is actually 5 cubed. So another way to get to the same answer would have been to say, okay, well, this is the cubed root of 2 cubed. Hope you can see that way squished in the corner. And this is the cubed root of 5 cubed. And remember, we just divide the powers by the index. 3 divided by 3 is 1. 3 divided by 3 is 1. So you'd still get 2/5, just taking a few more steps to get there. Okay. All right, so in this next question, we have the 5th root of the product 243 u to the 35th power. Okay, so if you remember that you can divide the power by the index, it actually is very easy to find the 5th root of u to the 35th. But we still have to deal with this 243 here. And I don't immediately recognize what's the 5th root of 243. I don't even know if it actually has a 5th root. So what I'm going to do is I'm going to factor it. I notice that 3 goes in evenly. Oops. That 3 has a mind of its own. Let's see. So 3 goes in 81 times. And 81 is 9 times 9. 3 is prime, by the way. And then these 9s are not prime, but they each factor into a pair of 3s here. So we have 243 is actually 3 to the 5th power. So when we take the 5th root of 243, we're really taking the 5th root of 3 to the 5th and the 5th root of u to the 35th. So what do? We divide the power by the index. So we have 3 to the 1st power and u to the 7th power. So 3u to the 7th. Okay, let's take a look at another scenario. By the way, in this problem we were assuming u to be positive, so we didn't have to worry about absolute value, but also the 5th root is an odd root, so you don't have to worry about it in that case either. Okay, now in this next problem, which I'm going to take a picture of here, maybe. I want to show you what it looks like in ALEX. Okay, so it says using absolute value to simplify higher radical expressions. So this is a kind of a hint there that you're not going to get on the test, that you might have to use an absolute value in these problems. And here's why. It says simplify each radical expression as much as possible. Assume that the variables represent any real numbers. Okay, so any real numbers means it could be positive and it could be negative. All right, so for part A, that really doesn't pose a problem, because the only time we need to worry about an absolute value is when we take the square root of x squared and we say, oh, well, if x was a negative number, that would turn out to actually be the positive version of x, or any other even root, fourth root of some unknown quantity to the fourth power, sixth root of some unknown quantity to the sixth power, something like that. Okay, but it doesn't matter with odd roots, because if you take the odd root of a negative, you're going to get a negative, so it works out nicely. So since in part A we have the odd root, odd index, we don't have to worry about having any absolute value. Okay, we can just, even though this is a weird looking expression, it's not just an x, it has a whole x minus 9 in parentheses here. The whole thing is being raised to the third power. We can divide the power by the index and we just say, okay, that's x minus 9 to the first power, or just x minus 9. Okay, on the other hand, here when we have y to the fourth and then the fourth root of that, since they're telling us y could potentially be negative, we divide the 4 by the 4 and get the first power, but we also have to be cautious because it could have been a negative number and we would be getting the positive version of it. So we write absolute value of y. Okay, remember you can type any questions into the chat box, and I'm going to keep going talking more about things that we have to do with radicals. Oops, I ran out of slides. Let me make some more. Okay, so one thing you may have noticed about all the radicals we've been dealing with so far is that the index went nice and evenly when divided into the power, and of course that's not always the case. I showed you one example at the beginning with numbers. Let's look at one example with variables. So for example, if you're asked to simplify the square root of w to the 13th power, although it's not written, there is an index of 2 here. And 2 does not divide evenly into the 13th power. So what can we do about that? Well, I want to remind you what we talked about in class last time, which was that you can actually write this as a rational exponent, a fraction in the exponent, w to the 13 halves. And I'm mentioning that because one way to think about this is that 13 halves is really 6 and a half. And so actually you could think of this as w to the 6th times w to the 1/2 power. right? Because if you add 6 and a half, you get 13 halves. And if you did that, then you would have w to the 6 times the square root of w, putting it back into radical notation. So this is one option. You could use what we learned about the power being the numerator of the exponent and the index being the denominator of the exponent, and actually rewrite it with a rational exponent. Or another way to do it without having to use rational exponents is, I always say you break off that extra w that's making the power odd. So what I mean is, think of w to the 13th power as w to the 12th power times w to the first power. So now we can break this up into two separate radicals. So we have the square root of w to the 12th and the square root of w to the first. This guy here, I call him the leftovers because the exponent 1 is not divisible by the index 2. So it doesn't, nothing happens with that. But this guy, 12 divided by 2 is 6. So we get w to the 6th square root of w, which is the same answer we got using rational exponents. Okay, let's look at a similar exercise, but it's a little bit more numbers and variables in it. So still the instructions are to simplify. By the way, I should have said in the previous problem, I'm assuming these variables to be positive. We're going to assume positive variables so that we don't have to worry about the square root giving us an absolute value. We're going to simplify, and we have the square root of 54 t to the 5th u to the 8th. Okay? So I think most people prefer to work with the radicals because we're just all used to it. We've done more with that in the past. So I'm going to use the second approach down here, and I'm going to split this up into two radical expressions being multiplied, where one is all the perfect squares, in other words, even powers. That 2, remember there's a 2 there, even though it's not written. That 2 goes into evenly, and then all those where it doesn't. But before I can do that, I'm going to analyze 54. 54's factorization could be thought of as 9 times 6. Neither of those is prime. So I would keep going until I get primes. 9 is 3 times 3, 6 is 3 times 2. So we can think of 54 as 3 cubed times 2. So I'm going to rewrite my radical real quick so we can just think of that 54 the same way that we do the rest of the variables. So we'll have 3 cubed, we'll have 2, we'll have t to the 5th, and we'll have u to the 8th. Okay, keeping in mind that the index that is unseen here is a 2, we want powers that 2 can go into evenly. So I'm going to split apart the 3 into 3 squared times 3 to the 1st. 2 can go evenly into 2, but not into 1, but that's okay. At least we have something that the 2 can go into. This guy is hopeless. There's no, the power is lower than 2, so there's nothing we can do with that. But t to the 5th, what's the largest even number less than 5? That would be the 4th power, right? So we're going to just break off that one factor of t to the 1st. And u to the 8th already has an even power that's divisible by 2. So now I'm going to split this into two radicals, and the two radicals are going to have all my even powers times a radical with all my leftovers. Okay, so what do I mean? 3 squared has an even power, but 3 to the first doesn't. 2 doesn't, so it goes in with the leftovers. T to the fourth has an even power, so it goes in with the even powers. And then over here, that extra t doesn't. So remember, that's a 4. For some reason, my ink pen doesn't like 4s. It always drags. Anyway, over here, we're going to take that index of 2 and divide it into each of the powers. So on the 3 squared, we have to divide the power of 2 by 2, we get 1. Or in other words, the square root of 3 squared is 3, right? And then the square root of t to the fourth, well, 2 goes into 4 twice, so that's going to be t squared. And the square root of 3 times 2 times t, there's nothing we can do with the leftovers but multiply them together, 6t under the radical. So that's how you would simplify that expression. And again, no absolute value because we're assuming the variables are positive. Okay, let's look at one more. It's got some bigger powers in it, and then we're going to look at adding and subtracting radicals. So in this one, we have to simplify. Once again, I'm assuming that we have positive variables. Okay, so we're going to look at the fourth root of 80 times s to the 19th times t to the 20th power. Okay, so for this one, we would like all of our powers to be divisible by 4 because the index is 4. But 80, we really need a factorization of 80 to figure out what powers it might have hidden in there. And 19 is not divisible by 4, and 20 is. So the power of 20 is good, but we need to do something with the 80 and the s to the 19th. So let's look at 80 and see how it factors. So maybe we would factor it into 8 times 10, for example. 8 factors further into 4 times 2. 2 is prime, 4 is not. 4 factors further into 2 times 2. 10 factors into 2 times 5. Both of those are prime. So 80 is actually 5 times 2 to the fourth power. Okay, so let's rewrite this radical where we have everything written as powers. It makes everything so much easier. So we have 5 times, we have 2 to the fourth power. That's supposed to be a 4. And then we have s to the 19th and t to the 20th. Okay, now let's focus on what is going to be in our powers of 4. We want powers of 4 in one radical. Or in other words, powers divisible by 4. And in the other radical, we're going to have our leftovers. Okay, so as far as powers of 4 go, 5 has a power of 1. That's less than 4. There's nothing we can do with that, so that guy's going into the leftovers. 2 to the fourth is already a power of 4. That's nice. 4 is definitely divisible by 4. But s to the 19th, okay, we need a number less than 19. We need the largest number less than 19 that's divisible by 4. So that would be 16, right? 16 is divisible by 4. So that means I have to break off 3 factors of s so that I can get my s to the 16th to go into my powers that are divisible by 4. That's an s, not a 5. And then I'll have my s to the 3rd in my leftovers. Now what do I do with the t to the 20th? I'm going to put that in with, I'm going to put that in with the radical that has all of the powers divisible by 4, or in other words, just powers of 4. So that's going to be t to the 20th. Okay, so last step, we're going to just go through and divide each of these exponents by 4. So 2 to the 4th, divide by 4, you have 2 to the 1st. 5 to the 6th, I'm sorry, not 5, s to the 16th. That is going to be 16 divided by 4 is 4, so we have s to the 4th power. T to the 20th, we'd have 20 divided by 4, so that's going to be t to the 5th power. And then we have all of our leftovers.
Mommy, these pants are bad.
Okay, so we're going to say 2s to the 4th, t to the 5th, times the 4th root of 5s cubed. And that's as far as we can go simplifying this guy. All right, so again, if you have any questions, please feel free to type them into the chat box. I hope you are all still able to hear me. I'm just going to check in with you. Oh, if I can get it to type. So if anybody could give me a shout out if you can hear me. All right. Let's talk about how, thank you, Ashley. Let's talk about how we can add and subtract square roots. Okay, so in this first example, the instructions just say simplify. And it says 5 square roots of 11 plus 6 square roots of 11. All right, so I want to direct your attention to a different problem that you already know how to work. Remember, that's what we like to do in algebra. We like to take something that looks kind of scary and compare it to something we already know. So we already know that if we had 5 multiplied by some unknown number x, and we wanted to add it to 6 multiplied times some unknown number x, that we would add their coefficients. And you may not think about it, but the reason why we're able to do that is because we undistribute the x. We factor it out. So factoring out that x, we are left with a 5 plus 6 behind, or 11. So that's why we add coefficients in variable expressions like this one. All right, so let's imagine this square root of 11, treating it the same way that we treated that x. So I'm going to factor it out, or undistribute it from the sum. So isn't it true that it would be the same as 5 plus 6 in parentheses times the square root of 11, right? If I multiplied that back inside, I'd get what I had started with. So I have factored out this square root of 11 over here. And what's left behind is, 5 plus 6 in parentheses is 11 square roots of 11. So it works exactly the same way. We're going to add their coefficients. What did we ultimately do? We took the 5 from the front and the 6 from the front. We added them together and we got 11. But the only reason that worked is because they both had exactly the same radical. Just like over here, we had an x, but it also would have worked if we had an x squared, right? It would have worked if we had an x cubed. Anytime we have the same exact number, we can just add the coefficients. So this would not have worked if I had, say, for example, 5 times the square root of 5 plus 6 times the square root of 6. Square root of 5 and square root of 6, not the same number. So you can't, there's nothing you can do with that. You would just have to stop here. Another example, what if I had 5 times and then I had the square root of 5 plus 6 times the cubed root of 6? Since the index, oops, sorry, I meant the cube root of 5, excuse me. So everything else is the same about the radical except the index. And even that is enough to mess it up. So what if we had 5 times the square root of 5 plus 6 times the square root of 5? Then yes, that one we can simplify by just adding the coefficient. Coefficient's the number being multiplied out front, because they have exactly the same radical. Sorry, my phone's going off here. Okay. All right, so let's look at some more complicated examples of that. All right, so in this next example, we have to simplify, and we're given negative square root of 32 minus 3 times the square root of 98. All right, now these are not like radicals clearly. 32 is not the same as 98, but we were told to simplify, so that includes simplifying the actual radical itself. So what we're going to do is simplify the square root of 32. We're going to do this using the technique that I've been using, looking for the prime factorization of 32. 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. So 32 is actually 2 to the 1, 2, 3, 4, 5th power. So I'm going to think of this as the square root of 2 to the 5th power. 98, we can do this a similar thing, right? 98, let's see, 2 goes into 98 49 times, and 49 is 7 times 7. So 98 is 2 times 7 squared. So we have minus 3, and then we have 2 times 7 squared. All right, let's go ahead and simplify each of these radicals. So remember, how do we do that? We want, since the index is 2, we want some power divisible by 2. So I'm going to break the 2 to the 5th apart into 2 to the 4th times 2. And over here, the 7 squared is divisible by 2, or rather the exponent on the 7 squared is divisible by 2. But the 2 to the 1st, there's nothing we can do with that. So I'm going to have my perfect squares and my leftovers. 2 to the 4th, square root of 2 to the 4th, square root of 2. Still have that negative tagging along out front there. Minus 3 times. I've got the square root of 7 squared, the perfect square, and the square root of the leftovers, 2. Now, square root of 2 to the 4th, remember the index is 2, so we divide 4 by 2, and we get 2 squared. So negative 2 squared, square root of 2, minus the square root of 7 squared is just 7, so we have 3 times 7 root 2. Or in other words, negative 2 squared, ooh, let me square that out. Remember, the power is only affecting what's immediately in front or to the left of it. So that negative is not affected, it stays there. So we have negative 4 root 2 minus 21 root 2. Okay, so now we see that since we've simplified the radicals, that we actually do have like radicals. Same index, 2, they're both square roots, and same radicand, 2 in this case. So what do? We just add their coefficients, or in this case, subtract, right? So the coefficient here is -4. We want to subtract 21. So -4, come on, pen. -4 minus 21 would be -25 root 2. And so that would be our solution. Okay? So when you're asked to simplify a sum or difference of radicals, you need to simplify to know if you actually have like radicals or not. It's possible I could have ended up with something that didn't have like radicals, and then I would just stop before combining like terms. Okay, everything we spoke about so far was in Objective 10, but I want to move on now to introduce you to a couple things in Objective 11 as well. So we are going to look now at special products of or products involving rational expressions, or radical expressions, excuse me. So for example, what if I want to multiply the square root of 3 times the square root of 27? So as long as the radicand, the number under the radical, is positive, you can just multiply these two roots together. And so we would have the square root of 3 times 27 is 81, which would be actually 9, right? We can do the same thing if we have something like the square root of 18 times the square root of 2 minus the square root of 3. Okay, so we can distribute this time because square root of 2 minus square root of 3, these are not like radicals, so we cannot just add their coefficients. But we can distribute this square root of 18. You might notice the square root of 18 is actually, can be simplified. So you have a choice. You could simplify it now and make it 3 root 2. Or you could just go ahead and multiply it through and then deal with the simplifying. I'm going to go ahead and simplify it now. So square root of 18 is going to be rewritten in a prime factorization like this. We have 2 times 9, and 9 factors into 3 times 3. So 18 is actually 3 squared times 2. So when we find the square root of 18, we're finding the square root of 3 squared times the square root of 2, or 3 root 2. So I'm going to replace square root of 18 with 3 root 2. Okay, and now I'm going to distribute this inside the parentheses. So we're going to have 3 root 2 times root 2 minus 3 root 2 times root 3. Okay, 3 root 2 root 2. Root 2 times root 2 is root 4, which is just 2. So we have 3 times, let's just say square root of 4, I won't skip a step, and then 3 times the square root of 6. Square root of 4 is 2 though, so we're going to say 3 times 2 is 6 minus 3 root 6. These are not like terms because the 6 on the left does not have a radical, so we're going to stop there. Now, some interesting things happen where when we actually multiply sums and differences of radicals together. Let's try that. Square root of 2 minus square root of 3 times 2 root 2 plus 1, for example. So in this case, notice that within each set of parentheses we do not have a common or a like radical. So we're going to have to do what we would do when we had variables. We're going to FOIL it out. Okay, so first times first, we would have 2 square roots of 2 square roots of 2. I'll simplify it in a minute. You can simplify it as you go if you want. We would have outer times outer, so that's going to be square root of 2 times 1 is square root of 2. Inner times inner is going to be minus 2 root 3 root 2. And then last times last, we're going to have plus, or actually it's going to be minus because it's a positive times a negative. So let me find my eraser here. So we're going to have minus 1 root 3. And then you just simplify. 2 times root 2. Root 2 times root 2 is root 4, which is 2. So 2 times 2 is 4. Plus square root of 2. And then minus 2 square roots of 3 times 2 is 6. And then minus the square root of 3. And none of these are like terms or like radicals, so you would just leave the answer like that. Okay? Now let's compare this to what happened there to one more problem, and then I'll let you go. And that is when you multiply conjugates. Do you remember we had with variables, we had conjugates like x plus y and x minus y? And if we multiplied them together, the middle term canceled out, and we got x squared minus y squared. Well, the same thing happens when we have radicals. We can have radical conjugates. Like, for example, we could have 5 plus the square root of 2 times 5 minus the square root of 2. And it will follow the same pattern. You're going to get the first terms. These are the same two terms, but with the opposite sign in the middle. That's key. So you're going to get the first two terms squared, 5 squared. And you're going to get the last term squared, square root of 2 squared, with a minus sign in the middle. You can see that if you FOIL it out, the way that I FOILed out the previous problem, that the middle terms actually cancel. So you end up with 25 minus 2. Square root of 2 squared, the root and the power cancel out, and we just get 2. So we're going to have 23 for that one. Okay, there's going to be, the reason why I wanted to hurry up and mention that before I leave is because there's going to be some problems where you have to do something called rationalizing the denominator, because we don't like to leave a radical in a denominator. So I just want to mention really quickly that you can use this technique to rationalize a denominator of choosing some special radical to multiply by. For example, if you had 1 over the square root of 5, you could multiply by the square root of 5 over the square root of 5, and you would get square root of 5 over 5. But if you had 1 over the square root of 5 plus 2, what you would have to do is to multiply by its conjugate, square root of 5 minus 2. And when you do that, you're going to get that 23 in the denominator and the square root of 5 minus 2 in the numerator. So you no longer have a radical in the denominator. All right, I know that was a lot of information. You guys have been very pleasant and very patient with me and all of the technical stuff, so thank you very much. I'm going to sign off now. I'll post a link to the recorded version of this video, and anybody who did not actually get to log in during the live chat can post a comment there as well. So goodbye, everybody. See if I can type here. Let's see. Keep studying hard. Remember, we have the final next week, and we will have our final Jeopardy review in the second class of next week. And the final will be due by Saturday, okay? Originally it was posted for Friday, but actually we have till Saturday. The testing lab's going to give us an extra day. All right, email me if you have any questions. Bye-bye.